So much for the introduction. Can you guys all hear me fine? Can you see my screen and my slides? And are they advancing? Yes. Okay, great. So yeah, today I'll be talking about machine learning based virtual diagnostics for electron beam phase-based prediction and particle accelerators. And let's see if that works. And the outline of my talk is as follows. I'll start by giving a sort of broad introduction, background, and motivation on machine learning based virtual diagnostics, and then spend the bulk of the talk just showing some examples of virtual diagnostics that we've trained and are using at SLAC. So I'll start with some examples from simulation data from two accelerator facilities here, the Facet 2 facility at SLAC, and then I'll discuss our first proof of concept of a virtual diagnostic that was actually trained on experimental data at the LCLS. Then I'll show some more simulations of a two-bunch operation at Facet 2, and I'll discuss some peculiarities of that, including specifically the effects of the measurement device on virtual diagnostic performance. And I will show some recent Facet data, and I will talk about optimization using longitudinal phase-based virtual diagnostics, uncertainty quantification, and some challenges and next steps. So starting from the background, for those of you who aren't sort of intimately familiar with virtual diagnostics and what they are, essentially a virtual diagnostic is a computational tool that is used to predict what the output of a diagnostic would look like when that diagnostic is unavailable. And it can be in the form of a fast physics-based simulation software or a machine learning model, but the essential workflow is the same. So you have some measured machine inputs that are typically non-destructive, like BPM readings, RF cavity settings, etc. You feed those into your virtual diagnostic, and that virtual diagnostic converts those scalars or image-based diagnostics that you can measure non-destructively into a real-time characterization of the diagnostic output, which I'm showing two examples of here. Excuse me for just making the video smaller. Two examples of here on the right. You can see, for instance, a multi-slit emittance measurement, which one might make to diagnose the transverse phase space of the beam, or a longitudinal phase-based measurement using a transverse deflecting cavity, which is what I'll focus most of this talk on. So there are there are challenges and sort of pros and cons of these two approaches. So with the fast physics-based simulation approach, one of the issues is that, typically for large machines, it's difficult to make simulations run quickly and also capture all the physics. So the execution of these simulations can take seconds to minutes. It can require high performance computing resources. And, even if you have all these resources on site, it often takes a lot of effort to actually replicate the machine behavior because there's just unknown unknowns, magnet misalignments, et cetera, which you just don't bake into the simulation a priori. And even then, let's say you nail these down, these can also change with time due to just drifts. So it's difficult to account for these with fast physics-based simulation. So machine learning model approach has some advantages, which is that, you can train neural nets, for example, offline from slow high fidelity simulations or online just using data from your machine. And once you've trained the neural net or your machine learning model of choice, it will execute very quickly so you can get shot-to-shot predictions. And it's basically why we're going to use this approach, and I'm going to discuss it throughout this talk rather than the physics-based simulation approach, although that can work, say, for smaller machines and for a slightly niche different scenarios. The joint benefits of these two is that once you have these virtual diagnostics operational, they provide both additional information for user experiments and an additional signal to feed it back on for longitudinal phase-based tuning, which is what I'll discuss in the coming slides. So that's kind of the broad background for what virtual diagnostics are and why they're interesting. To bring this down sort of more concretely to the two example facilities that we are going to discuss today, which is Facet and the LCLS, we're dealing with, as I said, these two problems. One is that if you're using destructive diagnostics to measure your beam, you can't measure the beam, sort of inserting a screen, and simultaneously deliver that to an experiment. And so, in that sense, the virtual diagnostic provides, extra data once you you've trained it up. But there's also a secondary problem, which is that if you want to diagnose intense beams with, say, screens or wires, you can actually damage physical diagnostics themselves. And I'm showing two pictures here on the left of broken wire scanners and holes drilled in aluminum screens, which are actually taken from a recent experimental run at the Facet accelerator, where we have a very highly compressed electron beam that's, say, only a micron in size and tens to hundreds of kiloamps in peak current. It can damage diagnostics in single shots sometimes. So the proposed solution, of course, is to try to use these AI or ML-based virtual diagnostic to predict the beam properties without intercepting the bunch. And I'm going to show this kind of schematic in a few slides' time when I discuss Facet and LCLS. But basically, this gives you an idea of the LINAC-based accelerator that I'm going to describe. For both Facet and LCLS is very similar. You have a photocathode RF gun that's followed by accelerating cavity sections, L0, 1, 2, and 3, and those are interspersed with bunch compression sections, BC11 and BC14. And these are important for our purposes because at each bunch compression location, because you're bending the beam emits synchrotron radiation, and that synchrotron radiation provides a non-destructive way to diagnose the bunch length. And we'll find that that's actually one of the most important non-destructive diagnostics to train our longitudinal phase-based virtual diagnostic. And so, the LCLS here, like I said, is the second linear accelerator facility, which we're going to show data from today. And it's very similar in layout here. There's just 2 bunch compressors instead of 3 as compared to Facet. And so again, as I just described, the motivation for us is to integrate these diagnostics into our control system to improve the understanding of beams delivered to experiments, reduce setup time, and consequently open access up to doing more science. So let's get to the examples and show you some data from simulation and experiment. Starting from a simulation study at Facet 2. So the way that we started training these virtual diagnostics before the accelerator Facet 2 was actually commissioned. So this is now already 5 years ago in 2018, is we have simulations of the machine that essentially scans some of the main machine parameters, which we expect to jitter around on a shot-to-shot basis. And what we did is we just did n-dimensional scans of these parameters within these ranges here shown on the right, and produce simulation data. And from this simulation data, we're particularly interested in the longitudinal phase space at the exit of the accelerator, which we typically measure here with a transverse deflecting cavity. And you can see here on the right, the longitudinal phase space from simulation, and then the prediction from our machine learning based virtual diagnostic that I'll describe in more detail in the next slide. And one important thing to stress is that we feed the inputs here that are shown in the boxes, the L1 voltage and phase, the energy at each bunch compressor, the L2 voltage and phase, and so on. We feed those as inputs to the machine learning model, and we're including random error to simulate the measurement accuracy here, which we would have on the actual machine when we're measuring these parameters. So in the first set of studies, what we did is try to predict, rather than the 2D phase space, we started by predicting just the bunch length, so a single scalar value, then moved on to the 1D current profile, and finally the 2-dimensional longitudinal phase space. And what we found is that, with this limited set of simulations, 5 to the 5 simulations, we're able to, with fairly high accuracy, predict the range of longitudinal phase spaces with good agreement with a small number of shots. So you see here on the right, the prediction score on the test set as a function of the fraction of shots in the training set, and the score here starts to drop only when the number of training shots is sort of less than 600, which is important for us because as we go further on in developing these diagnostics, we want to make sure that we can accurately train them within the parameter space that we want to operate in, without having to spend too much time actually training them on the machine, so that so that we can open up the access to the actual experimental users. Another important point to stress is that in simulation, of course, what we can do is just dump the macroparticle distribution, calculate the current profile directly from that distribution, and then feed that as input, as the ground truth in our predictions. But of course, we know that in reality, when we go to measure the current profile in the longitudinal phase space, we'll be using transverse deflectors. And transverse deflectors, have a limited resolution just by virtue of the fact that there's a limited streaking voltage you can apply to the beam, for a given size deflector. So we know that we will be producing shots that are very high peak current in reality, sort of 100 kiloamp plus, as I'm showing here in the top left plot. But some of these will be beyond the resolution of our TCAV measurement. And a robust way of tagging these shots is very important for us to be able to trust the output of the virtual diagnostic. I'll discuss a little bit more about that in a few slides' time when I talk about uncertainty quantification. So moving from 1D to 2D predictions, I showed already the result in the first slide 2 slides ago, but the longitudinal phase space prediction here is just a 2-dimensional version of what we do for the current profile. It's a simple, multi-layer perceptron, fully connected feed-forward net, and it predicts essentially each row in this image flattened down to a 1D array, and then reshaped into this two-dimensional image that you see here in the predicted columns. And the results, they show similar agreement between the neural net and simulation as we found for the 1D predictions. You see one example here on the top left of a shot that's got a bad prediction. The score is say 0.31, and just for reference here on the right, you can see that the histogram of the prediction score for each shot has a mean prediction score of say around 0.6, 0.62, which corresponds to something that looks more like what you see in subfigure B. So pretty accurate, barring some small features that are just computer generated and don't result in what's actually simulated. So one thing that we did, which is important for us, is to try to understand, rather than just seeing this prediction and saying, okay, this is good enough, now we move on, what is actually important? What are the diagnostics that are most critical for this prediction to be accurate? And in simulation, it's easy to do this, so you could just train the same neural net and remove some of the diagnostic inputs. And so what we see here in the plot on the right is that, for example, you get a mean score of 0.6, 0.65, maybe when you have all your diagnostics inserted. If you, for example, were to reduce some of these built-in artificial errors that we include, you can actually get better accuracy. So in this case, I mentioned the third bunch compressor at facet BC20. We know is going to have some fluctuation in the actual non-destructive measurement of the peak current. And so we know if we could improve on that diagnostic from the hardware side, we'd be able to do a better job with our prediction. That's something that's useful for our machine physicists to know. On the converse side, you see that removing some of the diagnostics has an adverse effect. So if, for example, we remove the non-destructive energy measurements after the bunch compressors, and/or these non-destructive measurements of the emittance, which we'll also have online as part of our diagnostic suite, we start to hinder the prediction accuracy. And finally, the last example shown in red, which is the most critical diagnostic for this kind of application, without the BC20, so the final bunch compressor peak current measurement, the predictions start to get very inaccurate. And so this kind of a sensitivity study is important, and I think we'll continue to do this as time goes on, as we deploy these tools on the machine. So moving on from simulation to actual experimental data. So what we did a few years back in 2018 is we took this same simulation study idea and actually just ran it on a real machine in experiment. And what we did during this experiment is we scanned 2 of the machine parameters, which most strongly influenced the shape of the longitudinal phase space at the exit of the LCLS LINAC, which is the phase of the first accelerating cavity. And we scanned that through several degrees, from -21 to -27.8 degrees. And the compression setting of the second bunch compressor BC2, in this case, from 1 to 7 kiloamps. And what that does is it generates a broad variety of longitudinal phase spaces In this case, much broader than the typical jitter that you would expect, on a single run that you've set up. But we wanted to try to essentially test the limits of this prediction. How many different longitudinal phase-space cases can one model predict accurately? And we see again that we get very good accuracy both in the 1D and the two-dimensional predictions. These are two separate models, one trained for the current, one trained for the longitudinal phase space, shown in the same plot. But another and maybe a more important thing that we learned is not just that we can also do this in practice, but there are some shots for which bad predictions occur, and we went to analyze these in detail. So we were trying to figure out, for most of these shots, the prediction is very good, but for some it's terrible. So why is this happening? And we looked specifically at the shots where this was happening, and you can see them. They're circled in this plot on the top left that shows the peak current of the measured and predicted profiles versus the beam full width half max. And we see that there are some shots with very high peak current that are strongly compressed, for which there's no overlap between measured and predicted. So they're just measured shots with high peak current that don't have a good prediction. And when you go to look at the prediction for those, you see that routinely the peak current is that the machine learning models predicting is around 2 kiloamps, whereas you're looking at anywhere between 4 and 6, much higher compression in reality. And what we found is that looking through the diagnostic inputs, the shots with bad prediction here were just a result of one of the diagnostics upstream misfiring. In this case, the BC2 peak current monitor. And what you see in the plot on the bottom left is if the BC2 peak current monitor is working properly, you would get a linear relationship between the peak current that you calculate from that non-destructive diagnostic and what you see on the transverse deflecting cavity. But for some shots, you just that diagnostic input is incorrect, and so because the machine learning model doesn't know any better than the inputs it's fed, it sees 2 kiloamps, so it predicts a 2 kiloamp current profile. And again, flagging these bad shots, for example, with a redundant diagnostic is important for trusting your virtual diagnostic prediction, because of course, when you're running this live on the machine, you're going to switch your TCAV off. So you need to know when your diagnostics have been misfiring. And in a similar vein to that, we studied for facet 2 a slightly different case, which has its own peculiarities, but it basically involves longitudinal phase space prediction, but for a 2-bunch setup. And you see that the longitudinal phase space here is very different from the ones I've been showing for LCLS and the single bunch facet 2 case. It has these 2 blobs. They're separated by about 150 microns. And they have a different peak current ratios between them. And if the movie will play, you'll see that as the natural jitter of the machine, RF jitter in this case, changes the phases and amplitudes of the RF settings upstream, you get both jitter in the peak current of each bunch and also time of separation jitter between the two. And these are very important figures of merit for Facet, the facility itself, because eventually you're going to send this 2-bunch profile into a plasma and do plasma wake field acceleration. And critical figure of merit for those plasma experiments to work is the ratio of the peak currents and the separation between the 2 bunches. So what we did in this study is, again, we trained the same sort of fully connected feed-forward net to predict the longitudinal phase space, but we included the transverse deflecting cavity streak in our actual simulated ground truth. So you see, we simulate the TCAV rather than just feeding the macroparticle distribution, and we're able to predict the TCAV, both the phase space and the current profile accurately. But what we can now do is look at the simulated TCAV current profile versus the actual current profile from macroparticles. If we were to have, say, infinite resolution or much better resolution with our TCAV, what would we actually see? And you can see that in single shots here, the black dashed line is the ground truth that we're feeding our machine learning model, which is the XTCAV streak measurement. And it can be very similar for 2 shots, but when you look at the macroparticle distribution, the peak current of the drive and witness bunches, as we call them, is actually is quite different. And this is also typified by these scatter plots on the right, which show, for low current shots, the drive and the witness peak current is predicted reasonably accurately by is measured accurately by the TCAV measurement, but there are those shots for which you're beyond the resolution. And so this is very critical point for us, and we need some additional input, like for example correlations with other diagnostics, to add confidence in the agreement between the measured longitudinal phase space and the actual longitudinal phase space at the interaction point. And so this is something that we've been working on, and I'll discuss it in the uncertainty quantification section. But before doing that, I wanted to say a few words about optimization. Optimization with longitudinal phase space virtual diagnostics can be done in sort of two different ways. So one of the first things that we looked at is we asked ourselves, well, now that you have a good model for what your longitudinal phase space looks like, can you just dial in a target, say choose a longitudinal phase space that you like, and take settings in simulation that are far from that target, but now use some conventional optimizer like simplex in this case to take you from those settings to your target settings by looping around, feeding back on the model. And it's something that we were able to successfully show, as you can see in these plots here. We start with some target settings that are shown by the purple star here. So if you look on the L1S and L2 phase scatter plot here, it's sort of -20, -40 degrees, but we start our initial settings way outside there, several degrees out. And even though the machine learning model is not trained within this range, we're trying to see if it can extrapolate to the correct settings. And the model does show that it can do this, and then it can take you sort of very close to the optimized settings, being very close to your target. And this is this is a comforting and sort of good result for us, because it shows us that we don't need to scan necessarily the whole parameter space here to get a model which is able to extrapolate successfully and also interpolate within the parameter range that we trained it in. And that means that basically this is better than just a simple lookup table for us. It's going to save us both time in setup, and it can do this broad range of settings. So one of the things that people are working on a lot these days is how to sample parameter space efficiently, and this gives us confidence that even if we sort of inefficiently sample with ND scans over a small parameter range, we'll be able to extrapolate outside of that with these kinds of virtual diagnostic models. And another study that we've done, for longitudinal phase space optimization is to kind of take the reverse approach. Rather than using a forward model now, try to use an inverse model that essentially takes your target longitudinal phase space, feeds that to a neural network, and the neural network suggests some machine settings that will generate that phase space. And what we did in this study from 2019 is that we combined this neural network-based warm start with a conventional optimizer like extremum seeking, and we had a sort of coarse-grained warm start of settings that the neural network suggests, starting from an initial distribution that you see here in the middle. First, we actually didn't use the neural network at all. We used just a local optimizer and try to get to this target distribution. The local optimizer gets stuck in local minima. But when you're using the neural network as a warm start, getting you close to the desired machine settings, then you're a lot less likely to fall into these local minima, and the optimizer feedback is able to achieve the desired longitudinal phase space. So this kind of sort of combined conventional optimization plus machine learning based prediction, it can improve the accuracy and the convergence of these kinds of backwards based system, and something that we plan on using for optimizing different longitudinal phase space setups for our experimental program going forward. Finally, I just wanted to say a few words about uncertainty quantification before opening it up to questions. So as I've discussed sort of a few times now, one of the avenues of research that we're sort of putting a lot of effort into is to try to make sure that when we have these virtual diagnostics online on the machine, we can actually trust their prediction. And I showed this example of the two bunch case for facet 2 to illustrate that. I'm showing the same sort of plots here on the left. You have two shots that have a current profile in blue, which we quote unquote measure in simulation, where we can arbitrarily set the resolution of that measurement, and then a smeared out distribution on the XTCAB that looks very similar between shots A and B, but is actually very different in reality. So one of the things that we can try to leverage in this case is looking at something which these two shots, these two different shots would have, would show difference in, and that's the emitted spectrum of radiation as these different current profiles travel through bends. So not just an integrated measurement of the radiation coming out of bunch compressors, as is typically used, but actually a spectrally resolved one. So you see for shots A and B, the higher peak current, more compressed beams will have higher spectral content at high frequencies. So training a spectral virtual diagnostic to predict the current based on this would give you sort of an orthogonal measurement of something that you might be able to say is now a shot that's beyond your TCAB resolution. And this is exactly what we did. So we sort of took these shots in simulation and we looked at the spectra, and we tried within a certain frequency band to integrate the spectral intensity. And we know that if we choose the frequency band properly to be basically at high enough frequency to capture the high peak current shots, there will be a behavior that's described by this plot in the middle, where if you plot the spectral intensity within that frequency band versus the peak current that's predicted by your transverse deflecting cavity, you'll see that starts to plateau at some point, in this case around 30 kiloamps, but the spectral intensity continues to increase because, as we know, shorter, more compressed bunches emit more high frequency. And so this is a nice way of tagging shots that are beyond the TCAB resolution. And it's something that will allow us to, infer, or at least set some kind of a boundary on the goodness of fit for our virtual diagnostics, and it's going to be important, especially for facet 2 for very high peak current applications. So we're looking to implement this going forward. I wanted to say another word about uncertainty quantification from the other side. So not necessarily trying to implement hardware upgrades like spectral measurements, but trying to quantify the intrinsic uncertainty associated with the virtual diagnostic model itself. And one of the things that you can do is sort of the very basic model ensembling, which is to train a virtual diagnostic and then using the same neural network, just randomly train it again, but reinitializing the weights. And what I'm showing here is the machine learning prediction and its variance from these ensembles for each pixel. And in this case, that can give you in a sense, it could give you a sense of the variance associated with the prediction itself. And while this is kind of difficult to interpret on the fly, we're working on how to incorporate this into sort of meaningful and rapidly interpretable figure of merit. Maybe say this, if the sum of the variance is high from a particular neural net, you would your neural net architecture, you would choose something else to maybe minimize that. It's something that you can use essentially when you're optimizing network architectures for your given application. And if you're interested in more others, this is just a movie that shows, for different shots, the prediction and its variance changing. But if you're interested in more applications of uncertainty quantification and specifically for virtual diagnostics, I recommend you read this this paper here by Owen Combry and Adi Hanukkah. They looked at multiple methods, including ensembling. They also did some studies of multiple neural net architectures for uncertainty reduction. So this is something that came out last year. It's worth a read. Okay, so finally, before opening this up to questions, I thought I'd just quickly summarize what I covered and didn't cover today. So I showed some examples of machine learning-based virtual diagnostics for longitudinal phase space based on simulation and machine data from multiple accelerators, really just two accelerators, LCLS and Facet 2. And I showed two examples of optimization with these virtual diagnostics with a forward model and an inverse model, and some examples of UQ, both in hardware improvements to reduce the uncertainty of a given prediction from virtual diagnostic, and also quantifying the uncertainty associated with models itself. I didn't say anything about transverse virtual face-based diagnostics and reconstruction, specifically tools that are being developed to non-destructively measure the emittance, which is, of course, a key figure of merit for high brightness electron accelerators. And I didn't cover retraining strategies. So how best to combine machine and simulation data and how often to retrain these virtual diagnostics to ensure good prediction accuracy over time. It's something we can discuss in the Q&A. Happy to do that. And also how to scale to complex operation modes. So these are parts of the next steps for this kind of work. I think a lot of work recently has shown that these virtual diagnostics are at least feasible in large particle accelerator facilities, sort of GV class, multiple accelerating sections, and also smaller facilities. So the key thing going forward is going to be improving robustness for these kinds of tools, and we really are aiming for deployment in routine accelerator operations. And these challenges of uncertainty quantification and retraining are going to be ones that we need to tackle. And I think having more beam time and dedicated studies it will be necessary to try to answer these complex questions before routine accelerator operation sees these integrated into classical diagnostic suites. And so finally, one slide thanking all the people that have worked on this. We have a pretty large group that's devoted to machine learning in the accelerator department here at SLAC. And also, I guess I'll advertise while I'm here. If you're interested in this kind of work or want to engage in discussions or collaborate, we're hiring, and we're also open to talking to you all. So please reach out to myself or Orly Edelin here at SLAC, who's the head of the machine learning group in the accelerator department. And so with that, I will thank you for your attention, and I'll take any questions.
Awesome. Thank you, Dr. Emma. I will re-emphasize that Radiosoft is not seeking those job applications. It is SLAC. So make sure you talk to Claudia Emma directly or Orly Edelin. First question we have lined up is, what is the loss function you use for training your LPS model? I've also sent you that in a direct message, Claudia, so you can see the text. Yeah,
so this depends. I mean, we tried, it's a good question. So usually we start with the sum of the RMSE on all pixels. But of course, when you're looking at, for example, these two bunch cases, this can be dominated by the drive beam, just because there's more particles in that bunch. There's a higher charge. Typically, it's 3-to-1 ratio in this case. So we experimented a little bit with custom loss functions and weighting, but yeah, for most of the examples I showed, that's the one. And you can, like I said, we didn't find major improvements. We did find some small improvements from tweaking the loss function, for example, by weighting n-to-1 between the two different bunches in this case, but it wasn't something too dramatic. So we sort of, yeah, that's what we've done.
Awesome, thank you. Second question is, the current distribution does not look completely Gaussian. How does that impact how you determine the FWHM?
Yeah, that's right. The current distribution is not a Gaussian, so we take the full width at half of the maximum. Yeah, even though the peak is not, it's not going to be related to the RMS in the same way as it is for a Gaussian. You can still calculate the full width, even if the distribution is spiky. So that's actually why we're using the full width at max rather than the RMS for these distributions, because yeah, they can have spikes in them.
Thank you. Next question. When performing ensemble predictions for UQ, how are predictions aggregated, i.e. mean/median? Do you identify and account for any outliers among ensemble members? And if so, were there many outliers? And I've also said
no, yeah, they're just aggregated. So we didn't do a study looking at outliers. So this is something that it's in the works. We would want to use larger ensembles for this. So it's not something that we've done yet, but yeah, that's a good point.
Thank you. We're coming up in 12:40, so we have time for one more quick question here. Last question we'll be able to address live is there a reason that you didn't perform the transverse emittance measurement?
So we do. The only reason I don't include it in this talk is because of time. So there's actually a project here that's being headed by Brendan O'Shea, who he got the DOE Early Career Award a few years back to develop a non-destructive emittance-based virtual diagnostic that uses machine learning. And I think that would be an entire talk in and of itself. But we are actually performing transverse emittance measurements routinely with this diagnostic that it's actually based on the interference of edge radiation between two edges of dipoles. So we can do this kind of measurement at each bunch compressor. And in fact, we do it both in the dog leg at bunch compressor 1, 2, and 3. And I encourage you to reach out to him for a lot more details, but we are performing that measurement routinely. So it's a project that's going on.
Thank you. And we'll sneak in just one more here. Would you expect this model to be easily portable to other facilities?
Yeah, so that is actually the hope. I mean, especially for sort of LINAC-based, say, FELs or LINAC-based facilities that look at, advanced acceleration, for example. There's typically the same sort of structure, like you have either a photo injector, it's usually a photo injector, and then there are accelerating cavities separated by bunch compressors. So fundamentally, the physics of the transformations that happens to longitudinal phase space is similar. It might not be exactly the same, like you might have higher charge in some places, which might make collective effects like CSR more dominant versus not. But the hope is to develop a suite of these models that are readily portable. And of course, we'll only know, how portable this is when we actually test, the same model on multiple machines, which we haven't done yet. But that's certainly where we want to be going forward.
Excellent. Thank you, Dr. Emma. That is all the time we have for today. So thank you again for coming to be our guest presenter. We appreciate it. Thank you to our audience for attending today. If you had to miss any part of it, we will send you a follow-up email with the links to the recording. And please join us next month for our February webinar. Bye, everybody.